Hey everyone, today we're going to talk about the first half of section 5.3. 5.3 is a long section, so I split it into two parts. Today we're going to start with the integral properties on the fundamental theorem of calculus, part 1. We talked about part 2 in the last section. Let's start off with some properties. Really quick, as a review of last section, let's do the antiderivative, these integrals. Well, what's the integral of 2x? It's an easy one. It's x squared evaluated from 2 to 4. This means plug in the top one. 4 squared is 16, minus 2 squared is 4. 16 minus 4 is 12. Okay? Let's compare that one to this one. It's almost the exact same problem, except the bounds are switched. But I'm going to follow my rules. This time the bounds are backwards, but I still plug in the top one first. 4, plug in the bottom one second, 16, and I get negative 12. So what's the general rule? What's this general integral rule? If you switch the bounds, it negates the answer. That's just the general rule, something you need to know. How about this one? Well, follow your rules. Antiderivative is x squared, evaluated from 2 to 2. Plug in 2, you get 4. Minus plug in 2, you get 4. You get 0. So what's the general rule here? If the bounds are the same, the answer is always going to be 0. Okay? If the bounds are the same, it's going to be 0. So that's just two of the rules. Let's try this one. What if I evaluate this from negative 2 to 1? X squared, negative 2 to 1. That's 1 minus 4, it's negative 3. Over here, this is x squared evaluated from 1 to 3. That's 9 minus 1, which is 8. If I put those two answers together, negative 3 plus 8, I got 5. Is there a better way to do this problem? Well, think about it. This is the area from negative 2 to 1, and this is the area from 1 to 3. Why can't I just put those together? The area from negative 2 to 1 and from 1 to 3 is the same thing as from negative 2 to positive 3. So instead of doing it as two separate integrals from negative 2 to 1 and then from 1 to 3, let's do it as one integral from negative 2 to 3. That's x squared evaluated from negative 2 to 3. That's 9 minus 4, which is also 5, which is what I got in the last slide. What's this saying? It's saying that the integral of each part added together is the integral of the total. There's a lot of little rules like this. If you want to see them, they're on page 269 of your textbook. Okay? If you want all the rules together. I'm not going to spend much more time on them because they're common sense. We're going to get into the first fundamental theorem of calculus. There's two applications of this. One of them is with algebra, and one of them is with graphs. What happens if we take the derivative of an integral? So what is the derivative of the integral of f of x? Well, what do you think happens to a derivative and an integral of f of x? And I need dx at the end. I always forget to put dx. Well, what about a derivative and an integral? They cancel each other out. So the answer is just f of x. That's the basic idea of the fundamental theorem of calculus. It gets a little bit more tricky. But this comes up in the multiple choice section of the AP test every year. In fact, I've heard it said that this is the most important idea in calculus. I don't know if I agree with it, but it's definitely one of the most. Here's the fundamental theorem of calculus. If you take the derivative of an integral, I'm going to change the t's to whatever that variable is. The bottom thing has to be a number. So the derivative and the integral cancel out, and I'm just left with f of x. Three things. Has to be the derivative of an integral. The top has to be a variable that matches the derivative, so x and x. The bottom is a number, a constant. So then what do? I just changed the t to an x. Let's take a look at this. Here's an example of the fundamental theorem of calculus. Step 1, it's a derivative of an integral. Check. Step 2, the top is a variable that matches this. Yep, they're both x's. Step 3, the bottom is a number. The bottom is negative pi. Is negative pi a number? Yep, check. So what do? I take the variable, put it right there. I don't change cosine to negative sign, or to positive sign, because derivative of an integral cancels itself out. Ooh, what happens here? The derivative of an integral, so we're good there. The top is x squared, not plain x. The bottom is 0, so we got 2 of the 3. I'm still going to treat it the same way. I'm still going to plug this in. That's going to give me cosine of x squared. But I have to include something. I have to include the derivative of the bound. What is the derivative of that top bound? What's the derivative of x squared? It's 2x. So what's my final answer? My final answer is 2x cosine x squared. Now, why didn't I do the derivative of the top bound in the last problem? Well, you did. What's the derivative of just the plain x? It's 1. It doesn't change the answer. So if what you're plugging in has a derivative, you have to include that. Ooh, this is close. Derivative of an integral, but they're backwards. There should be a letter on top and a number on bottom, but the letter's on bottom and the number's on top. So what do? We use one of the rules we talked about earlier. We change the sign. So this is the same thing as the derivative of the integral of 5 to x 3t sine t dt, but it's negative. So now the answer is going to be, just plug this in, 3x sine x. But it's negative because I had to switch the bounds. So if they're backwards, just switch it and change the bounds, or change the negative. So far we've had it pretty easy. We've always had one number and one letter, one variable. But what happens if I have 2 variables? We just split it into 2 problems. I don't know what's between 2x and x squared, so I just pick a number. The number I always pick is 0. So, the first thing I'm going to do is go from 0 to x squared. And then I'm going to go from 2x to 0. Now think about that for a second. If you go from 2x to 0 and 0 to x squared, that's the same thing as just going from 2x to x squared, which is this problem. Well, this one's pretty simple. Derivative of an integral, letter on top, number on bottom, plug it in. So that's 1 over 2 plus e to the x squared times 2x because of the derivative of the top thing. Over here, I need a d dx in front. Sorry, I forgot the d dx. This is okay, except it's backwards. So I've got to put a negative. Plug this in. 1 over 2 plus e to the 2x times 2 for the derivative of the 2x. Clean that up a little bit. That's 2x over 2 plus e to the x squared minus 2 over 2 plus e to the 2x. Don't overthink these problems. Just plug in whatever you're supposed to. If you have to change a sign, change a sign. If you have to split them, split them. But all we're doing is plugging stuff in. So that's fundamental theorem of calculus algebraically. And what's the big idea? Derivatives and integrals cancel each other out. Graphically. Take a look at this graph, take a look at the function, and take a look at what it means. This is a really tricky problem, and you really need to pay attention to what's happening at the beginning. Because if you don't understand the first concept, the next 10 problems that we do with this graph will not make any sense. What I'm saying here is that position is the integral of the graph. Position is the integral of the graph. So the graph is what? What function, when you integrate it, gets you back to position? What function, when you integrate it, gets you back to position? Velocity. This is a velocity graph. That is the most important concept for this. That's the fundamental theorem of calculus. If I integrate, I get position. What function, when you integrate, gives you position? Velocity. So everything we do is based on the fact that this is a velocity graph. What does this graph actually represent? It is not distance. The graph is not distance. The graph is velocity. Why? Because the graph is the integral. The position is the integral of velocity. So it's a velocity graph. So this graph is a velocity graph. Cannot stress that enough. Okay, let's find the position at 0. Well, let's just do some basic algebra. S of 0 means go to function S and plug in 0. So it's 0 to 0 of the graph. This takes no math at all. The bounds are the same. What's the area? 0. For the next one, position at 3.5. So I go up here and I plug in 3.5. Well, what is this? This means the area between 0 and 3.5. So what is the area here? What shape is that? If you're smart, you'll do it as a trapezoid. But if you're not, you can still do it as a rectangle and a triangle. Whatever makes sense to you. But I need to know the area there. I'm going to treat it like a trapezoid. The trapezoid is base 1, which is 2, plus base 2, which is 3.5, divided by 2 times the height. And the height of that trapezoid is 3. And that area is 8.25. The third question wants S of 8. So I plug in S of 8. So it's the integral from 0 to 8. But if you notice, this area can be split into two problems. The trapezoid that I just did minus this triangle. Why is it minus the triangle? Why isn't it plus the triangle? Because what kind of numbers are below the x-axis? Negative numbers. This is a negative velocity. And if it's a negative velocity, it means you're going backwards. You're losing. Well, the trapezoid was 8.25. We just did that. Minus the area of a triangle is 1/2. The base is 4.5. And the height is 3. Don't put -3 because the negative and the negative would cancel out. The negative and the minus would give you positive. to 3. If you do that, you get a total answer of 1.5. Now, why did I do this? Because I want position and I have velocity. Calculus, how do I get from velocity to position? You integrate. But I don't have a function to integrate. So what did I do? I have a graph. I found areas on the graph. What about these? I want to know the velocity at 0, the velocity at 3, and the velocity at 6. If you understand what this graph is, this is an extremely simple question. This is a velocity graph. Because this is a velocity graph, what's the velocity at 0? It's 3. What's the velocity at 3? It's 1. What's the velocity at 6? It's -2. Once you understand the fundamental theorem of calculus and can see that this is a velocity graph, the rest of it's pretty straightforward. Ooh, what about acceleration? This is a velocity graph. But what do you have to do to velocity to get acceleration? What in calculus do you have to do to velocity to get acceleration? You have to take the derivative. What does derivative of a graph mean? How do I find derivative from a graph? What I'm really asking you for is the slope of the graph. What is the, so in other words, this is saying what's the slope at x equals 1? What is the slope at x equals 1? That one's really easy. It's flat, so it's 0. This one takes a little bit more time to think about. How do I find the slope at 7? Well, normally we can't find the slope at a point. But what do you notice about this graph? It's a line. So how do I find the slope of a line? It's rise over run. How far did I go up? I went up 3. How far did I go over? I went over 4. So the slope of that line is 3/4. Why did I do slope? Because I have velocity and I want acceleration. I have to do the derivative. Derivative on a graph is slope. What is the average acceleration between 0 and 3? This is a question from the second chapter. Average acceleration. Average means 2 points. Acceleration is the derivative of the velocity, which is the slope. So I want to know the slope between the 2 points 0 and 3. Well, my 2 points are 0, 3 and 3, 1. So the slope between those two things would be 3 minus 1 over 0 minus 3, which is -2/3. Conceptual questions. Easy math. You have to understand, though. Average acceleration. Acceleration is the derivative of this graph, which makes it the slope of this graph. And average means between 2 points. What's the speed of the object at t equals 5? Well, if you remember that speed is just the absolute value of velocity, then this problem is easy. What's the velocity at 5? Remember, this is a velocity graph, so it's -3, which means the speed is the absolute value, which is 3. Easy question if you understand what the graph is. Where is S decreasing? Where is the position decreasing? What makes you go backwards? What makes you decrease? It's when your velocity is negative. You go backwards when your velocity is negative. Remember, this is a velocity graph. So I'm looking to see where this graph is negative. Where is this graph negative? Some people want to say here. No, that's not the graph being negative. That's the slope being negative. Where's the graph negative? From here to here. So this part down here is negative graph. -3.5 to 8. Do I include negative 3.5? No, because it's 0 there. Do I include 8? No, because it's 0 there. If I were to ask the other question, where is it increasing? It's increasing when the velocity is positive. This is the velocity graph. So when is the graph positive? The graph is positive from here to here. So from 0 to 3.5. Do I include 3.5? No, because that's on the axis. Do I include 0? Yes, because at 0 the graph is positive. Again, know what the graph is. Think about increasing and decreasing. That's where velocity is positive, velocity is negative. What's the absolute max? Well, a max occurs when you go from a positive slope to a negative slope, from a positive to a negative. Remember, this is the slope. This is the velocity. This is already the derivative graph. So I want to know where this graph goes from positive to negative. Where does this graph go from positive to negative? Right there. This is a velocity graph. It's a derivative graph. So I just look at the graph and see where it goes from positive to negative. Where is it concave down? Now let's talk about this. Concavity comes from the second derivative. This graph is the first derivative. So I really want to know the derivative of the graph, because that would be the derivative of the derivative. How do I find derivative of a graph? This means the slope of the graph. If it's concave down, this must mean where the slope is negative. So where on the graph is the slope negative? From here to here. From 2 to 5. Okay? What you just saw, guys, is a lot of material. And there's a lot of practice out there for it. We're going to do a lot of in-class practice for this, especially the graph part. Taking a derivative graph and being able to figure out the original, the derivative, and the second derivative information. Check out the mini lessons online. Check out the notes in class. Come talk to me if you have questions. Thanks.